Good morning, all. This is Dr. Ramakrishnan. I'm working as associate professor in SRM University AP, and I'm going to present my work, wake and radio-based medium access control protocol for wireless sensor networks. The objective of this work is to propose the wake and radio-based MAC protocol for wireless sensor network. It is a duty-cycled medium access control protocol, and there is two kind of duty cycled medium access control protocols available. One is synchronous duty cycled MAC, and another one is asynchronous duty cycled MAC. So in this work, we have proposed asynchronous duty cycled MAC because this asynchronous duty cycled MAC doesn't require any synchronization between time synchronization between nodes. So the time synchronization between the multi-hop sensor network is very difficult, and uh, it involves lots of overhead. So we have not gone for the synchronous duty cycle MAC. So we have designed asynchronous duty cycled medium access control protocol. And the implementation of the proposed protocol on CC430 based sensor nodes has been done. CC430 is a TA RF SoC chipset which has MSP430 processor core. It is a 16-bit processor core, and it has CC1101 RF core. Uh, Both the processor core and RF core are built inside a single chipset. So this is used as an RF SoC. So it it uh, uh, so this RF SoC is used in this particular work, and we have done the empirical energy consumption analysis. The energy consumption of the individual sensor nodes has been calculated by using the empirical method. Uh, so practically, we have measured the energy consumption. And then the motivation for this work is we want to design an ultra low energy consumption. We want to design a MAC which gives ultra low energy consumption for event driven sensor networks. So what we mean by event driven sensor network is the sensor networks which are triggered. The communication between the sensor nodes are triggered by the particular event. For example, if we deploy a wireless sensor network to detect the forest fire. So the forest fire is an event. Once the event is detected, then the communication is going to happen. So such kind of networks, if you want to increase the lifetime, then obviously it should reduce its idle listening. So it can reduce its idle listening by applying the duty cycling. So in this one, a very low duty cycle has been a very low duty cycle medium access control protocol has been developed. So the duty cycle which we have kept is 0.78 percentage. Duty cycle is a minimum duty cycle which we have made, and we have done the design with that. And we want to do the empirical energy consumption. So energy consumption, we even though the simulation we can have energy model and we can do the uh, energy consumption analysis by using the simulation and energy model in the simulation. Still, that is not accurate. So we have gone for the practical energy consumption analysis. And then the Mac which we have proposed is called low duty cycle Mac. We call it as low duty cycle Mac or LDC Mac. So in this LDC Mac, all the nodes are in the wake and radio mode, as it is asynchronous duty cycling. As it applies asynchronous duty cycling, in every node can go to wake up state or idle state at its own schedule. So each node can uh, have its own wake up sleep schedule. So the schedules are not dependent on other nodes. And when packet arrives, node wakes up and transmits a continuous short message followed by data. So whenever a packet arrives, immediately the node wakes up and it tries to send a short message. So the short message is sent because the node wants to, the transmitter wants to wake up the receiver. So the receiver may be in the sleep state, so it has to be waked up. So to wake up the receiver, we are giving the short message. This short message is given for time which is little more than the sleep time. So here the sleep time is almost 1 second is considered a sleep time. So this spraying of the short message or continuous transmission of the short message from the transmitter. So this happens for 1.3 seconds to make sure that we will be waking up the receiver, to ensure that we are waking up the receiver. So this spray time or continuous transmission time is a little more than the sleep time. So, and then the duty cycle is kept as 0.78 percentage. So that's why we call it as low duty cycle medium access control protocol. And then we go to the assumption. The first one is a common assumption, which mostly in the sensor networks we do use half duplex RF transceiver. It is common for most of the sensor networks deployment, and each node has same wake up and sleep period. So this wake up and sleep period for each node are same. So here the wake up period is 8 to 9 millisecond, and the sleep period is almost 990 or 992 millisecond. That's a sleep period. So if you compare this sleep and uh, if you compare the sleep and okay, then the RF transceiver has the addressing capability. So nowadays the commercial RF transceivers which are available, so all the RF transceivers has the addressing capability. So we can have a hardware address and we can address the individual nodes by using the hardware address. So that capability is available in most of the commercial RF transceivers available nowadays. And this is the LDC MAC packet flow. So this tells how our LDC MAC works. So here we have taken a transmitter and receiver, top uh, the top timeline which is shown. So uh, this is our transmitter, and the bottom one which is so this top one, this is our transmitter, and this one is our receiver. So this transmitter and receiver both goes to both goes in duty cycle mode. So it will be this orange rectangle that indicates the wake up period, and then this white So this TX and RX both are in the wake up radio mode. So it will be in the wake up state for a while, and this orange rectangle that indicates the wake up state, and then it goes to the sleep state. So when suppose that if the transmitter, if it is in the sleep state when the packet arrives, okay, at this instant, if the packet arrives, then immediately the transmitter will do continuous transmission of short message. So this short message is of 2 bytes. This short message is of 2 bytes. The first byte is the length byte, and the second byte is the target ID. The first byte is the length byte, and the second byte is the target ID. So these two things are given to the receiver. So these two bytes are the payload. Other than that, the preamble and sync words will be added. So we are not bothering about it as of now. So here this length byte and target ID, it is given continuously. So this short message is given continuously to all the surrounding receivers. So the intended receiver, when it receives this message, it will check whether the target ID matches with its receiver address. If its own address, if the target ID matches with its own address, then it stays on the reception state. So instead of going to the sleep state after the wake up, it goes to reception state. So it will be in the reception state. Before going to the reception state, it changes its hardware address so that the remaining short message uh, which has been transmitted by the transmitter, that will not be received by the receiver, because it has changed its hardware address. Once it changes its hardware address, so no longer the short messages are getting received in our receiver. Then the moment after the continuous transmission of short message, then the transmitter changes its hardware address, and then it transmits the data. It transmits the data. When it transmits the data is received by the receiver, as the receiver is already has changed its hardware address and waiting for the data. The data is received. So once the data is received, this yellow rectangle, so that indicates the acknowledgement transmission. Once the acknowledgement is transmitted, it is received here. So the gray rectangle here is acknowledgement reception. So the once the acknowledgement is received, the whole transaction is complete. So again, the nodes can go back to the wake and radio mode, that is the duty cycle mode. Before going to the wake and radio mode, it changes its hardware address and then it goes to wake and radio mode. So this is a unicast packet flow for LDC MAC. And then this is the LDC MAC packet frames. So here we have preamble and sync word. The preamble is 4 bytes and the sync word is 4 bytes, and we have the length field, and as far as the short message is concerned, we have the length and target ID, and these two things are appended in the receiver. So this is not the part of the packet. These 2 bytes are not part of the packet. So these 2 bytes are uh, appended in the receiver. So this over the air, these 2 bytes are not transmitted. So these 2 bytes are calculated in the receiver, and then that will be appended with the packet. So just for the illustration purpose, we have given this 2 bytes which are added in the FIFO by the receiver. Okay, so over the air packets are up to this one. So up to this one is over the air packets, and then sorry, over the air bytes. The bytes which are transmitted over the air is up to this. The 2 bytes are not transmitted from the transmitter. And then similarly for every case that for every frame, that is true. And here the data packet, we have uh, preamble and sync word, and then we have length, byte, and we have packet type. So this packet type is used to differentiate the data packet and acknowledgement packet. And here we have the destination address, source address, we have payload. So here we have used 37 bytes of payload because 64 bytes is used for the RxV4. So out of 64 bytes, as we want to restrict ourselves within the 64 bytes, we have kept the payload as 37 bytes. And of course, it depends upon the hardware in which it is going to get implemented. Of course, in even in CC430 itself, we can do the continuous transmission more than 64 uh, bytes before. That can be done, and more than 128 bytes also can be done. And here acknowledgement packet, if you consider the acknowledgement packet, here we have all are the same fields: packet type, destination address, source address, and optimal power level. So when the receiver receives the data, then it senses the RSSI, and it will tell, okay, this is the RSSI, and this is the optimal power level in which you can do the transmission. So that can be calculated here, and that optimal power level can be given here in the receiver. And then um, we have our sensed RSSI. What is the RSSI at which the data packet is received? So that data that is given here, and here this is the RSSI, and this is the RSSI for this acknowledgement reception. Uh, and this is your LQI for the acknowledgement reception. So this two are appended in the receiver of acknowledgement packet. So this is about the three packets which we are discussing here is short message and data transmission, data packet, and acknowledgement packet. Uh, so this is a sensor node, a CC430B sensor node in which we have implemented an LDC MAC. So uh, this sensor node is a off-the-shelf sensor node. It is from Olemix, and this sensor node has CC430F5137 RF SoC. So this SoC has 16-bit MSP430 5XX core, and this core has 32 KB flash and 4 KB RAM, and it has CC1101 RF core with wake and radio feature. So it has an inbuilt wake and radio feature, and the board is designed for 868 MHz. So the RF part of this board is designed for 868 MHz, and it has a PCB trace antenna. And at the indoor condition, we have done the range test, and it gives range more than 50 meters between two transmitters at the power level of plus 10 dBm, and the transmitter power level is 10 dBm and at 38.4 kb per second baud rate. And then the energy consumption, energy computation technique. So here we have to do the energy computation to measure the energy empirically. What we have done is we have measured the current consumption and the duration for which the current is consumed in a particular state. So that is measured by using a DSO. So we have used the DSO for capturing the current consumption and its duration for a particular state. For example, in the LDC, we have the wake up state. What is the current consumption at the wake up state? And what is the duration of the wake up state? All these things are empirically calculated by using the DSO. By using the digital storage oscilloscope, we have captured the signal. We have captured the voltage signal, which is proportional to current, and we have put a 1 ohm resistance, series 1 ohm resistance between the between the source or battery and our board, and we across the 1 ohm resistor we have taken the voltage to the DSO, and this voltage is proportional to this voltage is equal to the current. So suppose that if it shows 19.5 millivolts, then the current is 19.5 milliamperes. Okay, so as we have 1 ohm resistor, and the DSO is used for capturing the current consumption and the duration of current consumption for a particular state. And state is like wake up state, RX state. The wake up state is an RX state, and your sleep state and your TX state. So for all the states, we have measured the current consumption, and then the sensor node firmware measures the time. So for how much time we are in wake up state, and how much time we are in sleep state, how much time we are in transmission state. So that is measured by using the timer in the firmware, and that time value will be combined with the current consumption and power consumption or energy consumption of the particular state, and then we combine all these things and calculate the energy consumption. So the last point, it shows the expression here. This shows how an energy consumption for a particular state is measured. ES is the energy consumption of the particular state. It may be a wake up state, that is the reception state, that is wake up state, that is idle listening, or it may be a active reception state, it may be a transmission state. Okay, so it may be any state. So the voltage is constant 3.3 volts, and is is the current which is consumed. For example, during the wake up state, it is 19.5 milliamperes, typical reception 19.5 milliamperes, and the total time for which, for example, if I'm doing the simulation for 100 milliseconds, what is the total time for which the node is in the wake up or reception state? So that is calculated as Tt, and then with this parameters we will be calculating the energy for that particular state. So if we are measuring the energy of each and every state, energy spent on each and every state for a particular node, then we can combine all this energy and we can get the energy consumed by the node. And if we combine all the energy consumed by all the nodes, then we will get the network energy consumption. So the current consumption and duration of wake up period. So at the wake up period, so this figure shows the current consumption. So here we have 19.5 milliampere. So this height is 19.5 milliampere, and this height is 19.5 milliampere, and then this width is almost 9 milliseconds. So this duration and this current value, so this gives an indication that what is the energy consumed on the particular wake up state. So we all know that the voltage is constant 3.3 volts, and we know the current, and we know the time for which the current is consumed. So then we can calculate the power. Power is equal to V into I into T. So we can calculate the energy consumed for one wake up state. So when I'm doing a simulate, when I'm doing the implementation and I'm doing an experimentation for 100 seconds, so within that 100 seconds, how much time the node is in the wake up state. So if we calculate that, then we can accumulate all the wake up state current consumption, and then we'll get the energy consumption of one wake up state, and we can calculate the energy consumed for the total wake up states of uh, for the entire experimentation period. And then similarly, this is an energy consumed and duration for an active reception. When reception happens, that is, a short message is received by the intended receiver, and then it is going to RX mode. So it will be consuming the 19.5 milliamperes, almost 19.5 milliampere or 20 milliamperes of current. So here in this case, this duration is almost uh, almost 1.05 second. But for the calculation purpose, we have taken this time as 1.3 second. The active reception, whenever the active reception happens, we are assuming that the node is there in reception mode for 1.3 second. It is worst case reception time. Worst case reception time. So we are taking the worst case reception time for calculating appropriate energy for the reception. And then this is a figure which shows the transmission. So between each transmission, we have 500 milliseconds of 500 microseconds delay, and this transmissions. So this shows one transmission. After one transmission, 500 microseconds delay, and then another transmission, 500 microseconds delay, and this is how the continuous transmission happens. And here The topologies which are used in this experimentation is the topologies which are used for this node is a single hop topology, and it is a star topology which we have used. There is a base station, and so all the other nodes will be transmitting the data to the base station. So here we have the two node topology. One node is transmitting the data continuously, periodically to the base station, and here in the second experiment we have second topology, we have two nodes. Two nodes are transmitting to the base station, and here we have the three nodes which are transmitting to the base station. So this is a single hop star topology which has been used for this experiment. This is the experimental parameters. The RF baud rate is kept as 38.4, and we have used the frequency 865 MHz, which is license free in India. On Mac, we have used CSM SEA with Macon radio, and transmission power we have used 10 dBm, and carrier essence threshold we have used minus 95 dBm, and uh, the data acknowledgement size is 41 bytes, and 6 bytes is the data acknowledgement size. So the 41 bytes includes, along with the payload, it includes the header and the modulation. We have used 2 GFSK, and the packet integrity, it is 16-bit cyclic redundancy check. So here we are seeing the energy consumption of LDC Mac with two node topology. We are comparing it with the non-duty cycled Mac. So the traces which is there in the blue color. So this trace is for non-duty cycled. Um, this is for non-duty cycled non-duty cycled Mac, and this is for LDC Mac. So if you see the energy consumption of non-duty cycled Mac, so it is almost flat. So because the transmission, even when the packet interval time increases, that is, even if the traffic decreases, uh, the energy consumption will be almost the same, because the current consumption of the transmission and reception, it varies little bit. So 30% is the difference between the current consumption of transmission and reception. So in the reception, the current consumption is 20 milliamperes, and in the transmission it is 32 milliamperes. And as the reception happens for almost more time, so the proportion of reception duration is higher than the transmission duration, so that energy consumption is flat here. And as far as this LDC MAC is concerned, here when the traffic is so high, uh, here we are getting a higher energy consumption. So this higher energy consumption is attributed to increased transmission energy and increased reception energy. So when the traffic gets reduced, then the nodes uh, reception energy and transmission energy gets reduced, so we will be getting the reduced energy consumption. Here the overhearing avoidance doesn't play any role, because we have only two nodes. There is no a third node for doing the overhearing avoidance. So when the packet interval time is higher, then that means the traffic is low. So here also this is three node. So in the three node we have reduction in the energy consumption as far as the LDC MAC is concerned, because this can be attributed to the overhearing avoidance. So if we have the three nodes, so one node can do the overhearing avoidance, so that can be attributed to this energy reduction. Whereas here, this one, for the non-duty cycle MAC, when the number of nodes gets increased, then the total network energy consumption is getting increased. So because the node is always in the reception. This figure shows the current consumption for the 4-node topology, and this blue color trace, so that indicates this is the energy consumption of non-duty cycle MAC. This is for the non-duty cycled MAC, and this is for the LDC MAC. If we consider the energy consumption of non-duty cycle MAC, so it gets increased because as the number of nodes gets increased, the total network energy consumption gets increased as far as the non-duty cycle MAC is concerned. Whereas in the LDC MAC, even when the number of nodes gets increased, the node density of the network gets increased, uh, it 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 causes the reduction in the energy consumption, which is attributed to overhearing avoidance. And here we have here we have the energy for the 4 nodes. The energy consumption of the LDC MAC gets reduced, and we all know, and from the figure it is observed that when the traffic gets decreased, then we will have a slight decrease in the energy consumption also. Topology, and then we have we have energy savings due to overheating avoidance. Here we are showing this red trace is for the 2 nodes. So for the 2-node case, there is no overhearing avoidance because one node is a transmitter and another node is an intended receiver. So there is no the overhearing avoidance which happens because there is no third node. So here, if the third node is available, then the energy savings, so that is drastically high when the traffic is high. And if the 4-node case is concerned, the energy savings are quite high at the higher traffics. So this figure shows when the traffic is high, the energy consumption due to overhearing avoidance that gets increased when the number of nodes or the node density becomes higher. So that is what has been indicated here. So obviously the overhearing avoidance gives better energy savings for sensor networks. In conclusion, here we are giving the figures or the percentage energy conservation which we got out of a particular either duty cycling or overhearing avoidance. How much is the maximum energy conservation we got and at what conditions? So that has been stated here. And here in this work, the LDC MAC has been proposed and implemented in CC430 based node, and the energy conservation of LDC MAC compared to the non-duty cycle MAC is 92%, 94%, and 97% for the 2, 3, 4-node topologies. So obviously, if we go for the number of nodes are higher, obviously the energy conservation becomes higher because of the overhearing avoidance, and then the energy conservation due to overhearing avoidance goes up to 46.11 percentage. It goes up to 46.11 percentage for high traffic with uh, 4-node topology. So this shows that in the future work we want to extend the LDC MAC to have the power control, and we'll be implementing the power control. So already in the frame we have given the right we have given the parameters which are required for the power control. So that will be exploited for developing a power control, transmission power control for the further energy conservation. And we will be doing this power control by using RSSI and LQI. RSSI is receive signal strength indicator, and LQI is link quality indicator. So these two are available in CC430. By using that, we will be finding the optimal power, and the transmitter will do the transmission at optimal power to conserve the energy further. So that's it as far as this presentation is concerned. Thank you.